Very good.
Okay, so Dave, please start.
Okay, I'll go ahead and get started here. This, let's just see, got it, yes. Has to give me a warning that it's recording me here. In any case, I'm going to give you a quick overview. I'm not really quite sure I've got the topic perfectly set, but what I'm going to talk about is actually running the spectral mapping atmospheric radiative transfer smart model to generate radiant spectra. And so I'll run through this in kind of two segments. The first is just a quick, fairly high-level overview of what the model is trying to do and what kinds of input it needs in order to do that job, and a little bit on what the output looks like. And then what we'll do, just to kind of shake things up and also to give you a little bit more of a direct idea of what it looks like to run this model, I've got a couple of examples queued up. I think one of the things that people who have used the code have found the most useful in the code is going through the log files that are created by the model as it runs, and that helps to kind of tell you what the model is thinking as it moves along and what kind of information it needs, and that's kind of that's a useful thing to look through. So, okay, we're going to be talking about this model called SMART that everybody knows about. SMART stands for Spectral Mapping Atmospheric Radiative Transfer, and you'll see what that means as we run through this a little bit more quickly here. First of all, the basic idea of this model is to generate radiant spectra for realistic scattering, absorbing, emitting planetary atmospheres. And that works for the planet you live on. It also works on exoplanets around M-dwarf stars. It basically is a general purpose, full physics radiative transfer code that's been designed to basically just do one thing, which is generate radiances and that kind of information, radiances, fluxes, and heating rates. So the basic idea, if you, the approach that we've used here is to use something called the full physics approach. The full physics approach uses the best available information about the optical properties of the atmosphere, the viewing geometry, that kind of information in order to generate a spectrum. It makes a minimum number of approximations, but it still will make approximations in order to move through the spectrum a little bit faster. And the real problem is that when you look at a spectrum like the solar spectrum here shown in the upper right in the figure here, or the thermal spectrum shown next to it, these spectra actually cover several wave numbers, or several thousand wave numbers, let's say, are tens of microns sometimes in their span. And we have to divide the solar part of the spectrum here, or the stellar part of the spectrum, or the thermal part of the spectrum, into something like 1 million different spectral regions to resolve the incredibly rapidly varying optical properties that we have across these spectral ranges. And what that does is in a typical model, what you'll do is you'll take those optical properties, you'll generate them on a high resolution spectral grid that completely resolves the spectral dependence of these properties, and then go and do a calculation, a radiative transfer calculation at each of those spectral grid points. That can get expensive, especially if the radiative transfer calculation you're performing is an angle-dependent multiple scattering calculation, which can take a second to do or more on even the fastest computers. So, and if I have 10 to the 7 spectral intervals to hit, which is a kind of common amount to do a bolometric spectrum of a planet, it'll take a lifetime to get through this. And you've probably all heard me say things like, you want to remember what the experiment was doing, over the time it takes to run. Otherwise, you're kind of lost. So you need to speed these things up a little bit. And so what we do to speed things up, speed up SMART, is to take a couple of shortcuts, but they're still fairly straightforward shortcuts, and I'll go through those quickly. So once again, we've got an intrinsically very difficult problem here. We're going to use spectral mapping methods to solve this problem while maintaining the best available information we can about the atmosphere, including the vertical structure of the atmosphere and its wavelength dependence. We're going to take into account all of the absorbers and emitters and scatterers in the atmosphere as best we can. And that includes the gases, any airborne particles like clouds and aerosols, and also a surface that can have varying surface properties. So, okay. What are we actually going to be doing here? Well, we're going to be calculating, and shown here in a little bit greater detail is a solar radiance spectrum for the Earth for a bunch of different surface types shown here. You can probably guess them if you look at them. The blue line is scary enough. It turns out being the ocean. The brown line is a desert. Basically green. In green here, you see a forest basically showing a nice chlorophyll red edge here at 700 nanometers and so forth. In the thermal, the main features in the Earth spectrum are the CO2 15 micron band, the ozone 9.6 micron band here, and of course the water that suppresses the emission at most longer infrared wavelengths. So what do we do with SMART to actually calculate these spectrum? Well, we start off just as if we were going to calculate the spectrum absolutely from first principles. We go and gather all of the optical properties together, and we populate a high resolution spectral grid with maybe 10 million points on it across these ranges. So that's the starting point. So we define a spectral grid that completely resolves the wavelength dependent optical properties. And I need a resolving power of between 1 million and 10 million to do that, okay? To actually get that job done. And so I'm going to completely resolve the wavelength dependent optical properties of the surface, all of the gases, the clouds, the aerosols, everything that contributes to the radiation field. I'm then going to identify spectral grid points within that 10 to the 7 spectral grid points I have. Guess what? You're going to find that some of those grid points are very, very similar to other grid points in that very large array. So what I'm going to do is to try to identify the grid points that all have very, very similar optical properties. I'm going to combine those together into a smaller number of spectral grid bins. And now I'm going to go and do a multiple scattering calculation once, or actually it turns out being a few calculations you perform in each bin. And now once I've done that, I have radiance values, angle dependent radiance field. I'm going to map that back to a high resolution monochromatic grid, just where I took them from. Okay, and that generates a spectrum that looks, the idea is to generate a spectrum that looks indistinguishable from a spectrum you would have generated if you had just calculated, done a monochromatic multiple scattering calculation at every grid point. Okay, so that's the basic idea here. The kinds of speed ups you get for using this very, very simple method for binning is a speed up of typically, the way I used to say it is you get about a factor of 100 speed up for about for the cost of about a 1% error. Nowadays, I think we pushed the error down to maybe a couple of tenths of a percent for that same compression factor of about 100 in speed up. And that's significant. To put this in perspective, on a fast workstation, to produce the spectra you see in front of you would take about a week on a fast workstation if I did it using a direct monochromatic multiple scattering calculation with about 8 streams in 4 up and 4 down streams in a multiple scattering calculation. If you take that week, that's a fairly long period of time. If I now reduce that to a time period that's 1/100th of that time, now we're talking about something you can get done a few times a day rather than once a week. Okay, so you can get a lot more work done. And at the time that this system was built, that was a big step forward because nothing like it really existed at that time. It's been around for a while, and there are lots of papers that have been published on this, starting, I think the first one we ever published on this was Meadows and Crisp, which was a paper on the emission from the Venus night side. The model had just more or less come online. I had been building it while Vicky was making new observations of the night side of Venus. And so we combined our forces here and wrote a paper back in the mid-90s on that. And since that time, there have been a lot of papers, as you can see, that have used this model. Most recently, I should say early in its life, it was used for primarily Venus, Earth, and Mars, and a little bit for Neptune. We processed a whole lot of Neptune observations from HST using this model. But then since the turn of the century, we've been using it primarily for exoplanet studies. And for those who are familiar with my regular day job, we did not use this, we did not adopt this approach for OCO, the OCO and OCO2 and OCO3 emissions, because quite frankly, with even a couple of tenths of a percent uncertainty or error introduced by the radiative transfer code, that was just too much. We basically need radiative transfer codes with accuracies better than a part per thousand for that application. So we use direct full physics models for that. But the spectral ranges that we're covering are very narrow, 3 bands, each about 1% wide. So it basically is fast enough. Now, so one of the real important features of a model like SMART is that it resolves the vertical structure of atmospheres. Now, I say that, and I've been saying that for like 30 years now, but in reality, it doesn't really quite resolve things as well as it should. In particular, what we do is we take a vertically inhomogeneous atmosphere. Here we have the Earth, and we have a vertical structure for the Earth, with the troposphere, the stratosphere, and the mesosphere, for example, shown here. We're going through about 4 orders of magnitude in pressure in that. I've got a cloud, a homogeneous or probably a mid-latitude stratus deck shown here in this model as well, that we have included in this particular case. So what I would do with this is I would divide this atmosphere into about say 75 to 100 layers and do multiple scattering calculation in that atmosphere. Now, the reason I'm going to pull my punches and say we don't quite resolve atmospheres perfectly is that right now, with the current version of the model, we do not do non-local thermodynamic equilibrium. Our current gas absorption cross-section code does not support that. It only actually calculates the cross-sections for gases in local thermodynamic equilibrium. So for the Earth's atmosphere, sitting up here at about 60 kilometers, which is the top of the domain shown here, is about as high as we can go. We can change that. We can go back and update the absorption cross-section codes to include non-local thermodynamic processes. We would then have to run perhaps an iterative solution where we would use an initial guess for the gas cross-sections, populations. We would run a calculation, we'd get a radiance field from that. We would take that radiance field that would adjust the gas cross-sections and the population of states of the molecules in the atmosphere. We would then rerun the model, and hopefully after 2 or 3 steps, and this is everybody's experience, the thing would finally converge, and we could actually start doing non-LTE. The other thing about this model is that this model currently uses a fairly crude approximation for sphericity in a planetary atmosphere. More sophisticated methods are available today, including one that we're in the process of incorporating into SMART, but it's not quite there, which does a complete pseudospherical treatment that's much more complete than this. Now, so once again, this shows the vertical temperature structure in this particular calculation, spanning a very wide range. Other calculations that we've done have included hot Jupiters. We've actually done some brown dwarfs with this model so far. Basically, you can put any temperature structure you want in this model and any other optical properties. Down the figure down on the bottom here on the bottom right shows an example for the Earth's atmosphere, showing the vertical structure of the mixing ratios of the gases that we have here. And these are volume mixing ratios. You can specify these either as volume or mass mixing ratios in the model itself. It doesn't really care which. And then once again, just showing the kind of resolution that we use in the model. And once again, there are about a dozen gases in this particular calculation. That's a common number. Okay, so basically the kind of information, we have a thermal structure file. That's the first thing we're going to read in. You'll see me reference that a little bit later on. The thermal structure file determines the vertical structure of the atmosphere and the actual level structure. Whatever level structure you have in your thermal structure file is the level structure that will be adopted for the rest of the calculation. If you give it gas mixing ratios, you can put those on any vertical grid you want. You can even specify them for a single layer if you want. And what the model will do is interpolate those mixing ratios, gas mixing ratios, to the vertical structure grid. It makes a couple of assumptions in that process. It assumes that the mixing ratios are interpolated to the level structure, assuming that the mixing ratios vary linearly with the log of pressure within each layer. Okay, that's the assumption made. So you want to have enough vertical layers in your model to resolve any very kinky structure in any gas mixing ratios that you have in there. So that if you do within a given layer, if you assume that the variation is linear in log pressure, it's good enough. So I make a lot of those assumptions throughout this model. This model uses essentially trapezoid integration for everything. So the basic assumption that it makes in any layer is that things vary in the, whatever vertical coordinate I've chosen, vary linear in that vertical coordinate through that atmospheric layer. So that's the way this works. By the way, if you have any questions, just butt in. These are just, I'm just going through a lot of this pretty fast. With clouds and aerosols, I have the approach that I have in there right now dates back about 30 years in terms of design, and it's a non-ideal approach for a lot of atmospheres. At the time, the data sources that I had were specifying, they would say, you have a cloud and it has this optical thickness. Okay, so they were specifying things in terms of optical depth. And so I used that as my vertical coordinate in the current model. In the future, we're probably going to change that so that we can either keep the same basic structure for clouds and aerosols, or we can specify number densities, which are much more like what we have in the specification of the vertical structure of the gases. And then the vertical structure of the gases and the aerosols can be specified pretty much the same way. I can make assumptions then, like right now, the basic assumption is that if you tell me that I have a cloud, the way you do that is take the cloud and resolve it into a bunch of different layers. In each layer, you give me a differential optical depth, which is the optical depth across that sublayer of your cloud. And you give me the single scattering albedos and so forth of the particles over that particular sublayer. Okay, so that's the way the model thinks now. But it kind of has a preconceived idea of what an optical depth is, and you're giving it an optical depth. Now, what I'm doing here is I give you the optical depth of the optical depth, vertical distribution of optical depth at one wavelength, at some reference wavelength, and it'll ask you for what reference wavelength that is. And so when you get that reference wavelength, let's say you measured the optical depths of your atmosphere at 0.6 microns. Now, why did I do it that way? It's because when the Pioneer Venus probes went through the Venus atmosphere, and when Nolenberg probes were going through the Earth's atmosphere back in the Pleistocene before most of you were born, that's the way they reported the data. You went through a cirrus cloud, it had an optical depth of 0.15, okay, at 600 nanometers, okay? So I had that information. And then what I would do is go off and use a single scattering particle code. And I would say, okay, I know what a cirrus cloud is. It's a bunch of, I'm going to simulate my cirrus cloud as a bunch of 100 micron long by 10 micron wide hexagonal cylinders. And I'm going to calculate the wavelength dependent optical properties for an ensemble of those particles. And I'm going to make sure that I take the extinction efficiencies at 600 nanometers, where I know the optical depth, and I stack it into the cloud with that 600 with the right optical depth. I specify, okay, I've got a cloud layer here. The cloud layer has an optical depth of 0.15, and that optical depth is made up of cirrus cloud. So it goes and grabs the cirrus cloud single scattering file. And what I've essentially done there is a separation of variables where I separated the vertical structure of the cloud with the wavelength dependent optical properties of that cloud. You see, so that's what I'm trying to do here. I do that for clouds, I do that for aerosols, and I specify these clouds and aerosols, as you'll see in a moment, in the context of something called a particle mode. And typically what a particle mode is it's a distribution of particle sizes. And I've actually calculated the optical properties for that mode. Okay, so you'll see some more of that in a minute. Okay, so I've separated out the vertical dependence and the wavelength dependence of my clouds and aerosols. I have essentially done the same thing for gases. I've done the same thing basically for both gases and aerosols. Now, the wavelength dependent optical properties I need for all of these things are as follows. For scattering by atoms and molecules, I basically only include Rayleigh scattering at this point. There are ways to include other kinds of scattering in this. Rayleigh scattering is a nice optically conservative scattering, so it's straightforward to include. One could also include Raman scattering, as another thing one could include here. That would also require that you run an iterative series of calculations where you would run a calculation, you would calculate the distribution of optical depths, you'd calculate the light distribution, and then you would actually take a fraction of that and say, okay, that's shifted by a certain wavelength forward and backward, and you put it back into the calculation and run it a few times. I do not include Raman scattering at this point, nor any other kind of air glow phenomena of that kind, non-conservative scattering by gases. For atoms and molecules, the kind of wavelength dependent information that I need, Rayleigh scattering is really straightforward. What I calculate are the Rayleigh scattering cross sections for that molecule. I don't have the Rayleigh scattering cross sections or ways to calculate them for any molecule. I do have them for about a dozen different molecules, and mostly the common ones that are in planetary atmospheres, such as hydrogen, helium, oxygen, nitrogen, those kinds of things, carbon dioxide. I have them for all of those things and a few more. And the model can basically put together a bulk atmosphere that includes most of the main pieces and calculate Rayleigh scattering for that atmosphere. The way I calculate a Rayleigh scattering for the atmosphere of Venus and Mars in particular is I basically just give it a pure CO2 or 96% pure CO2 atmosphere with about a 4% Earth atmosphere sitting on top of it, which is the oxygen and nitrogen. And that does a pretty good job of simulating the cross sections for Rayleigh scattering. For atoms and molecules, I need the wavelength dependent optical properties of those. There are different kinds of optical properties that need to be included here. For infrared calculations, the main thing that we usually think about are vibration rotation calculations. These are basically the absorption and emission by molecules that occur as they vibrate and rotate in various different ways in the atmosphere. And we're going to have to specify those. We're going to run a line by line cross-section model that's going to generate absorption cross-sections, and the particular model I have right now called LBL-ABC is one that some of you have already used. This actually is also an ancient piece of code that it's in desperate need of an update. But at the moment, what it does is it calculates temperature and pressure dependent cross-sections for gases. It uses a strange unit of centimeters squared per gram. That way, instead of multiplying it by a number density and a path length, I basically multiply it by a concentration in grams per square centimeter in each layer. That was a decision I made back when I was in graduate school, and I haven't had a chance to go back and revise it. This will be changed in the near future, as will the structure of these files. And I'll keep this old unit, of course, but I'm going to mainly look at centimeters squared per molecule, a simple cross-section kind of calculation. That would be more sensible because that's in fact what's used for just about everything else. Electronic transitions. Okay, as all of you know, electronic transitions change more slowly in wavelength. They typically are seen in the blue and UV parts of the spectrum, and the code takes that kind of information into account. We use a different, basically the vibration rotation transitions. If we put those files out as ASCII files or as simple readable tables, they would be enormous. They would take up a terabyte of storage for just water alone. So what I typically do is compress those as much as I can into binary files. I'm going to change that in the near future too, to read them in as either HDF or NetCDF files. That will compress them down just as much, but give you a more common way of reading them. Right now, you have to know exactly how I wrote those bits out in order to read them back in, and that's not quite that's not considered to be friendly these days. So I'll change that as I update the code. Electronic transitions, they're written out in the opposite order of the vibration rotation transitions. The vibration rotation transitions are written out in order of increasing wave number. The electronic transitions are written out in order of increasing wavelength. I blame Bill DeMoore on that back when he was putting together the first sets of cross-section tables. In the UV, he wrote them out in wavelength order. That's fine with me. The code can read in that order just fine. But I have a fairly stringent formula, just as for the vibration rotation transitions, the electronic transition files can get quite large. And so there's a fairly strict, they're just ASCII tables, but there's a fairly strict format on those files. Once again, I'm going to change that also to a netcdf file. So you don't have to know what the format is. You just have to know where the variable is in it. And then finally, the collisionally induced absorption or pressure induced absorption, people refer to as CIA. It's not that CIA. These files are specified as in terms of wave number and then temperature dependent values in this absolutely terrible unit of centimeters per amigat. I'm not even going to try to describe that here. In any case, I'm probably going to turn that back into something that's more of just a binary absorption coefficient. That will at least give the users who are not familiar with these ancient laboratory measurements a way of proceeding. And then let's see, clouds and aerosols. Once again, we define different particle modes. That's a historical artifact as well. What some people like to do, and nowadays we have bin microphysics models like Karma, and they're going to go and generate a number density matrix in every level of your model, where you have some big particles, some small particles, and some ratio. And people like to use those. And so they're going to call that a particle mode. And if they have 75 layers in their model, they're going to go and actually calculate 75 particle modes. You can do that. The model will take it. But that's not the way I'd originally thought about this, partly because I always kind of thought of things in terms of, I initially started thinking of things in terms of things like Earth clouds and Venus clouds. And there I had a small number of particle modes. On Earth, we have cloud droplets, we have raindrops, and we have ice particles. And those would be separate modes, for example. On Venus, we have modes 1, 2, 3, 4, or 1, 2, and 3, let's call them 1, 2, and 2 prime and 3. And they have different particle sizes. They're made of different, they have a different composition in principle for each particle mode. And you can go and generate a separate optical property file for that. In the old days, me scattering and certainly non-spherical particle scattering was so expensive that if you could generate the optical properties for 5 or 10 particle modes, that was all you had the time to do anyway. Nowadays, that's pretty trivial, and we can put lots and lots of different modes in there. So I'm probably going to change the basic structure and input of this just to make it more flexible. We'll keep the same structure just as we always do as an option, but then the user can also pick maybe a little bit more less confining approach for doing this. In this particular case, and you'll see a file later on, we basically line up the optical properties for aerosols, the wavelength dependent optical properties for aerosols for each mode as basically flat files, tables, which list wavelength, and then the extinction cross section or the extinction efficiency. The model will use either one interchangeably, single scattering albedo, and either particle phase function, which is expressed as a Legendre polynomial moments for that phase function, or an asymmetry parameter. If I get really, really enthusiastic, I will eventually make this broad enough so that the user can put in either the angle dependent phase function values or the moments, either one, and the code can figure out what to do with that. Right now, it basically just takes the moments, the Legendre polynomial moments. Those have to be calculated offline.
Dave, can I ask a quick question?
Yes, please, Elliot.
If you find a huge forward scattering phase function and you want to simulate it with Legendre polynomial moments, do you find that you need an enormous number of moments?
Yes, if you do it directly. What I would do instead is this model has a delta M method built in. So what it will typically do is truncate that forward peak, simulate it as a delta function, which means it just takes it out of the optical depth, and then fit the rest of the phase function with Legendre polynomials. And, for even let's say a 200 micron hexagonal ice crystal, for example, or a raindrop at visible wavelengths, where you would have this monstrous forward peak, that works pretty well with about 8 streams. Okay, now that's unless you really get fanatic and you're asking, what is the brightness of the intensity of the radiation field half a degree off the sun's disk? Okay, because then you're going to be looking right at its forward scattering. Now you want to go and do a 220 moment expansion of that forward phase function and go and do it right. But that calculation is going to take some time. I hope that
Thanks.
answers your question.
You
Okay.
bet.
And then surface reflectance. The way that surface reflectance is currently specified in the model is you can either choose a Lambertian reflectance for your surface, and then basically then it just asks for the wavelength dependent albedos of the surface. So just a flat file with wavelength in one column and the reflectance or albedo in the second column. And you can tell it which column, it doesn't even matter. Or you can actually ask for a non-Lambertian albedo. It only includes a couple of choices right now. The only one that's been extensively tested is the Cox-Monk ocean model. And there it's a little bit restrictive as well. At this point, the only Cox-Monk ocean model that I routinely include in the calculation is a Cox-Monk water model. If you want to make an ocean of liquid hydrazine, it doesn't have the right refractive index. And so one of the things that we're going to be changing as we move forward is that the user will be able to put in a wavelength dependent index refraction file, and it'll go and redo the calculation and give you the right wavelength dependent scattering off the surface of your ocean. But that's something that has to be done in the future as well. The other property we have to specify is if you want a solar or stellar source, you have to tell the model where to go and find one. And typically, what we do here, the only kind of external source that the model currently accepts is a direct beam source. It doesn't assume any external thermal sources above your atmosphere. And so what you can do is go and put in your, you can actually put in only one solar spectrum at this point. I can imagine situations where in exoplanet worlds, you might actually want to include a couple at different solar zenith angles. That would be kind of fun. There's no real limitation in doing that with the model, but right now the way you would do it is run two separate calculations and add them together. That's the way it works. The light from the two stars doesn't interfere or anything. The best solar spectrum out there right now is the TSIS-1 hybrid solar spectrum that Odell Coddington and her team at LASP has just produced. I don't even have that. I don't even have the highest version of that set up for running in SMART at the moment. But it's just head and shoulders above the approaches that I've used in the past, where I've kind of done what Odell has done here. I've knitted together solar continuum files from one source, usually from a space shuttle flight or from a satellite, to get a top of the atmosphere solar spectrum, with line files either from Bob Carews, and these would be completely synthetic stellar atmosphere files, or observed line files like those that Jeff Toon has generated. So I would then generate a solar spectrum from that. I've got several of those lying around with different spectral resolving powers and different levels of accuracy. I'm basically going to suggest everybody throw them all away and go and get Odell's spectrum, because it's actually for the sun. Now, when you're dealing with another star, we've also got stellar spectra for a variety of different stars. A pretty good library of those are being built up by Vicki and her team at University of Washington. And I encourage you to use those as we need them. What you'll find is that very often the UV part of the spectrum, the part that's beyond the left side of this graph over here, is very poorly specified in a lot of areas, and that's largely because a lot of these spectra of stars were taken from the Earth, where we have little atmospheric windows that cover a small range of wavelength, and so we don't have complete spectra in the UV. Some stars have been observed with STIS, and we have those spectra. Other stars have been observed with earlier UV instruments, and we have that information for whatever wavelength range they actually use. But once again, cobbling together your stellar spectrum is a critical part of this as well. Okay, now given all that information, I've got all of these different kinds of information. I've got, let's say, a bunch of gases that are on a really, really manic looking grid, like the one shown over here, where I maybe have 1,000 points between 6160 and 6300 wave numbers here, where I'm going to be resolving the optical properties of the gas. In addition to that, I might have some aerosols where I could, over this range, the aerosol optical depths aren't going to change by enough that you could actually resolve them beyond just a simple line with 2 points, defined by 2 points, for example. Okay, so that grid might have a lower resolution. It turns out, and I might also have a thermal source. I have to, if I have thermal emission within the atmosphere, I have to resolve that source, it turns out. It turns out I don't have to resolve the sun. Because what I'm going to do is I'm going to do a radiative transfer calculation with it for my external source, assuming a unit emission, a unit brightness at the top of the atmosphere for my sun in my initial calculation. And then I'm going to go back and I'm going to play the same game I'm going to talk about in a minute to define the spectral grid. And actually scale that one by whatever the actual radiance was. In this particular case, 2.5 watts per square meter per wave number, or per micron or whatever it is in this plot at that particular point, and then down here 1 over here and over here 10th, whatever. I'm going to just scale the whole radiance bundle that I get out of the model at that wavelength by the solar flux. It's a simple scalar multiply. Okay, so I don't have to include the spectral dependence of the sun in my radiative transfer calculation, and I can still get a radiative transfer calculation with arbitrary spectral resolution that resolves everything, including the sun, at the end. But now to do that for the things I do have to include in the radiative transfer calculation, I have to include the optical depths of everything in the atmosphere, the gases and the aerosols. I have to include single scattering albedos. I have to include phase function information, and I have to include that at every grid point. And they're all on, and gases and aerosols and the surface are all going to be given to you on different wavelength ranges. And one approach that my colleagues in OCO started with was to just put everything on an equally spaced grid. It's really easy to do and use the same grid for everybody. And then you come out getting a 2 gigabyte file for your surface albedo, and it's changing by a couple of % over the full spectral range, right? It doesn't make any sense. So what I do is I generate a spectral grid on the fly. And the grid that I calculate is something called a lowest common denominator grid. And the idea there is this is done internally to SMART. You don't even have to know about it. You can just give it the grid structures that you've got, and it'll figure it out. And what it does is if it has starting at a given wavelength, it just looks through all of its optical property files. It finds the first wavelength that's within the spectral range that you've specified, or just outside that range, actually. It decides that it's going to make that a grid point. It just picks that point. And then it interpolates all of the other points, all of the other optical property grids to that point, just using linear interpolation. It assumes that internally to every optical property file that you've resolved things well enough, okay? That linear interpolation works. And so let's say then it just grabs, and then it goes and looks through all the files and it says, what's the next point? It grabs that point and it says, okay, I'm going to take that point too. Now I'm going to interpolate all of the other points in the optical grid files to that point. You might notice this one had a point here and here, but I interpolated a point there. Okay, so no big deal. It's real straightforward. I just generate the grid that I need to resolve everything. The only constraint on that grid is that if 2 points are closer together than 1 part in 10 to the 7, I don't even bother. That's too close. That's the kind of the internal grid spacing that I adopted early in this game. You can change this value it requires that you can change it internally, and you can change it to 10 to the minus 14 if you want, and it'll still be fine. It'll just generate the grid on a slightly. It'll put a few more grid points in there. Okay, so it basically generates this grid over the full spectral range you have. Like I said, over the solar plus thermal spectral range for Earth or Venus or Mars, it's about 10 to the 7 points. Okay, so that's the first step. And then at every one of those grid points, I go through and I calculate the cross sections, the optical depths, which are just the integration of the cross section times the number density times the distance to each layer of the atmosphere. I calculate the single scattering albedos. Once again, it's just taking into account the sum of the scattering cross sections divided our optical depths over the sum of the extinction optical depths. And then I calculate the phase function, or if I'm using asymmetry parameters, the same way. I basically just use a scattering cross-section weighted value for the phase functions for the particles. Okay, so those are the properties you calculate at each of those 10 to the 7 grid points. Now I've gone and generated this really kind of big file, and I'm going to generate it as I go along, by the way. I'm going to generate one wavelength. I'm literally going to calculate radiance, bin that calculation, or bin that value and forget about it, or keep it as optical properties. I'm actually going to keep it, it turns out. And I've done that at all of these grid points, but that turns out being fairly cheap compared to the cost of actually doing a monochromatic multiple scattering calculation. So what I'm going to try to then do is cheat, and I'm going to go and actually use spectral binning. And there, I'm not going to go through this in detail. I've talked about SMART in the past and how it actually works. But basically what we do is we run through the spectrum. We find that there, as we go through the spectrum, it has a lot of structure in the optical properties. And if you pick, to say, the red line or the green line here, you might have a particular value for the vertical distribution of differential optical depth or single scattering albedo. And what we do with SMART is we say, I'm going to generate bins that are basically determined by that particular optical depth profile, vertical profile, plus some difference, plus or minus, from that profile. And anything that I see anywhere else in this spectral range at any spectral grid point through there, and like I said, there are about 1,000 points across this particular range here. Anything that looks the same within these bounds is added to that bin. Okay, that's what the binning process does. It's just the simplest, most straightforward sorting approach. And so each bin is defined as a differential optical depth plus or minus some range, a single scattering albedo plus or minus some range, a scattering asymmetry parameter plus or minus some range. Turns out I sort on scattering asymmetry parameter, not on the full phase function, which can have 220 moments. But just on the first moment of the phase function. And that turns out working pretty well. And then surface albedo, I do the same thing. And if you have multiple surface pressures, I have to deal with that as well. So once again, I go through the whole 10 to the 7 spectral range and will basically run this binning operation. Then I have my values in my bins. And so what I'm going to do then is calculate radiances essentially once or twice, it turns out, within each bin. So this is one bin, this is another bin, this is another bin. The differential optical depths are quite different from bin to bin in this particular case, but within one bin, they're all within some range. And so what I do is I actually calculate not just the optical depth, I actually calculate two quantities. I calculate the I should say, don't just calculate the radiances, the angle-dependent radiance field for that bin. I calculate the angle-dependent radiance field and the spectral Jacobians for each of these with respect to each of these quantities. So the Jacobian with respect to optical depth, that's the rate of change of radiance with a change in optical depth. The rate of change of radiance with a change in single scattering albedo. The rate of change of radiance with a change in the asymmetry parameter, and the rate of change of radiance for a change in albedo. And I do those linear changes within each of these narrow spectral ranges that I've specified in each bin. Okay, so that's what I do. And what I'm going to do in the end is I'm going to actually use a Taylor series expansion to actually define, I remembered the optical properties, all of those optical properties for every single spectral grid point. So actually I go and calculate my small number of radiances and my smaller number of bins. And for each bin, then I take the radiance values and their Jacobians and then say, okay, over here at wave number 213.4, you were assigned to bin 17. So I'm going to take that bin radiance value, I'm going to adjust it with the Jacobians for the actual optical depths and single scattering albedos and phase functions that I had there. And I'm going to map it over back to that spectral range. And I'll hit it with its top of the atmosphere solar flux at that point. I'm done. Okay. I've just generated a radiance with SMART. Now, just to get into some physical things, since we're running out of time here, we got a little bit of a late start. We have a series of output grids. We have a spectral output grid. You can either put out that full high resolution grid that you've just generated that resolves everything that your input data resolves, or you can actually convolve that spectrum with a instrument line shape function of some sort, and then resample it any way you, well, not just any way you want. It turns out you have to use a fairly regular way, either a constant wave number or a constant resolving power. Those are your choices in the current code. If you want something else, tell me and I'll think about it. And then in addition to the spectral domain, the output grid also includes a level domain. You can ask for radiances at the top of the atmosphere. You can ask for radiances at the surface, or you can ask for the radiances at any vertical level in the system. Up to 10 levels can be output in a single run. That was just a simplification that I made to keep the memory down to a manageable size. If you need that number to be increased, we can just change a parameter and it's a bigger number. When you run the calculation, you can run it for a single solar zenith angle or an array of solar zenith angles, and will generate output for that, whatever that array is. This is just an example of, if I want to scan an entire hemisphere, I might use this array of values. Because the model uses a spherical atmosphere, you do actually get sunlight when the sun's sitting on the horizon. Okay, so you can have 90-degree zenith angles. Now, then we have angles, and this gets a little bit complicated, but the bottom line is that the angular output for your fluxes is just up and down. That's all you get. But for radiances, you have a range of options. Here, you can either ask for the radiances to be output on the Gaussian angles, which are the internal computational angles. I often do that because then I can use Legendre's polynomial interpolation to interpolate that external to the model to any other angles I want. Alternatively, you can actually give it a bunch of user-defined output angles. I think they just have to be monotonically increasing, and the model is happy with you, and it'll generate the output on those. Like, for example, you might say this range of zenith angles you want your radiances to be output on. The same thing with azimuth. The model internally uses Fourier modes, and it just maps those Fourier modes to any output angle you want. And so I typically will give it a range of angles. Notice that that range of angles is only covering 0 to 180. And that's because everything in this model assumes everything is basically left side, right side symmetric in the phase function. We haven't included any particularly pathological phase functions here. If you do, once again, just make sure that you ask for the azimuth information. It'll go and calculate those azimuths for you just fine. Okay, by the way, I don't think I've ever tried that. So if you'd like to be the guinea pig, if you're at the top of the atmosphere and you're looking down at your planet, it only tells you what the upward fluxes from the planet are, right? It doesn't tell you what the downward fluxes are because you're above everything in the atmosphere. So it basically just gives you the range of outward going rays. It get the actual structure of the output file is wavelength, wave number, the downward solar flux at the top of the atmosphere if you've specified that you want a solar flux, upward solar flux, diffuse flux at the top of the atmosphere. And so this is the downward direct flux. This is the upward diffuse flux. You can actually do that ratio and get a very nice albedo out of it right away for the spectral range that you actually use. And then it'll give you the radiances for each of the upward streams. And so it's shown here is this is an 8-stream model. I have 4 upward streams. It'll give you those numbers, the radiances at each of those streams. If you have a number of azimuths, it gives you the zenith angles 1 to 8 for azimuth 1, 1 to 8 for azimuth 2, whatever for the next azimuth and so forth. That's the way they're arranged. The radiances are you tell it what output units you want as a part of your input, and it'll give you radiances in those units. If you're at the surface, you might be interested in both the upwelling radiation field and the downwelling radiation field, so the model will print out both. So it basically gives you the full 360-degree radiation field. As shown here, it gives you all of the streams over the full range of angles in zenith angle, and then it gives you the values of each azimuth angle you've asked for at each of those zenith angles. So that's the thing that I included there. So what I wanted to do at this point was to jump out of this presentation and jump into a walkthrough of a log file. But we're at the end of our hour and it's Friday afternoon and we have to free all the slaves. Yuck, if you want, we can just pick this up at another time. everybody's really quiet. I know you're still there. I can hear you.
Yeah.
I have no problem with you. It's better for you
desperately
next
trying
week.
to find my unmute button. Okay, I was afraid I might be causing any noise in the background, so I mute myself, but now I cannot find my
Mute
my
button.
mute button. Okay, so what I suggest is this time is out. You can give a short demonstration, and then it says I would have people who have experience in using this code, like Jia Zhen, be your teaching assistant, and Jia Zhen can run some cases.
Yeah.
And if
That's-
Jia Zhen have questions, Jia Zhen can get back to you.
That's probably a good way to proceed. My usual approach is to teach one person how to use this, and the idea is that that person has to teach the next person. So yeah, Johnson, you could be the guinea pig here. But let's see that I don't want to keep anybody over on a Friday afternoon, even for that. So I was going to suggest, Yuck, that we skip until whenever we meet next. When are you planning to meet next?
Unless there's something urgent or fantastic next Friday at 4 o'clock from the AGU, I'm going to have this meeting as usual next Friday, unless it conflicts with something really interesting from the AGU.
Unfortunately, that's the OCO session. So
Oh my God.
they put us again right at the end of the week, and it spans the whole day. And so I'll be tied up in sessions this time next week. And then I think our calendar kind of falls apart in a fairly catastrophic way. With the following week is Christmas Eve, and I'm not going to do this in a Santa Claus hat.
Yeah.
And then the next is New Year's Eve, and
yeah. We went through this before last week. That's why we stick. This is the only window, 1 hour window we have. So what I have said, what I have in mind is that you give Jia Zhen this. Jia Zhen knows how to download the whole package from your website. Is that right? Or
I think I gave you a distribution sometime in the recent past. I would assume that would be what John Shen is using. Or are you using the GitHub? Are you accessing the GitHub site at University of Washington?
Jia Zhen, are you there? I see. Jia Zhen has disappeared, I think. But that's fine. I will get hold of Jia Zhen. Yeah, he has a working version. I want to make sure this is the version from the University of Washington. Or send me the link just to confirm to make sure this is the canonical version. And then Jia Zhen can give a demonstration.
Is it not possible to do it on a different night? It doesn't have to be Friday necessarily.
Well, one of the possibilities, Chris, is that we might be able to do this we might be able to do it maybe in the same time slot on sometime the week after next, that would throw it into the week of that would be the 20th, 21st, or 22nd. I know a lot of folks will be going away then, but it really is a question of the individuals here. And then the other possibility is to do it on one of the days, the 28th, the 29th, or the 30th during that week.
Yeah, I think people have family commitments. For example, I have a full-time job because it's my grandchildren will be here. I will be a full-time chauffeur and entertainer. Okay.
Now,
so I suggest maybe Wednesday the 22nd, tentatively Wednesday the 22nd at 4 o'clock.
That's possible.
Okay, so let me mark it down in my calendar. Okay. Okay, 4 o'clock, Wednesday the 22nd.
Should we take a straw poll to see if everybody can?
Yeah, can
I know I
everybody
can.
do it? Can all the people who are interested in SMART be able to do it?
I can.
Yeah, in that case, I think,
Okay with me.
yeah, we, for once, democracy works. You know, we are
That's an
stuck with
optimism.
we are stuck with the worst possible way of government, except for the alternatives.
Yes, that's the,
Yeah,
that's the,
yeah.
so I'll go ahead and scribble in the Caltech meeting on my calendar, but you probably want to send it around on the
I will
22nd
send
at 4
it.
o'clock.
Yeah, as soon as I get in touch with Jiazhen, I hope to have Jiazhen's demo, or Jiazhen will be ready to help people to do things. Is it before this time? And then there are questions after they have played with the code. They can ask you. Also at that time, you can keep your case of demo.
Yeah, let's see. I might run into a little problem there in that I'm officially not supposed to export the source code. I'm just about to get this thing into public domain, but it's not there yet. So.
And will it be there, say, January 1st next year?
I doubt that as well. There's quite a lot of paperwork that has to go in to get it thrown through that system. And I'm still kind of struggling with that. So, but the executable you can all use. It's not a
in that
problem.
case, that's good enough for demo. You see,
Yeah.
for the other code, it's only important if you want to go into it and make changes. And the number of people who has to do that is tiny. I mean,
Well, the other thing I can do is work with either Run Lee or with Danica.
Right.
And they can actually generate executables that will run on your machines.
Right.
And then not distribute the source code.
Right. That'll be fine.
And that keeps us absolutely legal.
Yeah.
And it still gives everybody the tools that they need.
Right.
That's the way we do it on VPL. We distribute source code. The source code only gets sent to U.S. citizens. The executables get sent around the world.
Okay.
So.
Yeah. Okay. Okay. Thank you very much. I guess we'll see you guys at the EAGU. I guess you must have like 10 sessions on CO2.
Yeah, there's a session. There's at least one session every day on
Right.
either CO2 or SIF or something to do with inventories or something.
Right.
I'm presenting on Thursday, and I'm a co-author on something every day.
Right. Yeah. Okay. So thank you very much. So goodbye to everyone except Danica. Danica, can you hang on for a minute?
Yes, I have to be somewhere at 5:30, but I can stay for 20 minutes.
Yeah, I only need you for a few minutes. Okay.
Perfect,
Okay. So
okay.
bye to everyone.
Take care, all.
Okay. So Danica, first of all, you have to tell me how to get out of this recording.
Oh yes, if you click, there should be like a stop sign near your share
Yes,
screen.
I see it at the top. It said pause. Okay, I'm going to hit